Today we're going to continue chapter 7 and we're going to go into a little bit more detail about the structure of an atom. And the first thing I want to highlight when we talk about the structure of an atom is this word probability. So when we draw pictures of an atom, a lot of times we draw them like this because that's the easiest way to draw them, but that's not actually what we think the atoms look like. What we are able to do now is to plot the probability of an electron's path. And what I mean by that is if there's a very high chance that an electron exists in that region, we can shade it dark. If it's a low chance that the electron exists in that region, we shade it light. So if you remember the analogy from yesterday, if you throw a bucket of tennis balls up onto a bunch of stairs, like in a basketball gym in the stadium or in the football stadium, they can only land on the stairs. They're not going to land halfway between the stairs. And it's the same thing with electrons. They can only exist in certain regions around the nucleus. However, they're not all circles either, and we'll talk about that in just a minute. But we call them clouds because when we plot these using images and using fancy technology, we end up with these shaded regions. So we call them clouds. So that's the first thing, is you need to be able to explain why they exist as clouds and not as specific circles like Bohr originally thought. Schrödinger is the scientist who's famous for this idea. He calls it the quantum model of the atom, or quantum mechanical model. And this is the idea that we can plot the probability of where electrons exist, and we can shade it, and we get these clouds. And we talk about these shaded regions as orbitals. So the next thing you need to be able to do is explain in your own words what the word orbital means. And first of all, notice that they are not circular orbits for the electrons. This is not like the solar system where you have an orbit for the Earth that goes around the sun in a circle. It's going to be more of an area of probability for where the electrons are going to be located. So make sure if you're ever talking about orbitals in an essay AP question that you can explain it as the probability of where electrons are located. Heisenberg's uncertainty principle kind of goes along with some of the stuff we talked about yesterday, but he says it's impossible to know exactly the position and the momentum of a particle at a given time. The more you know about one, the less you know about the other. And so that's why we call it probability instead of certainty. We don't know exactly where the electron is because we can only know one of these at a time. And that's also can be used as an explanation on an AP exam for why we only know the probability, is because we can only know one of these in detail at a time. If you take upper level chemistries, you'll go into some fancy calculations about the wave functions, and you'll talk more in detail about that. For this class, we don't do a whole lot of detail about that. Just understand, again, number 2 is kind of describing it, that electron density is going to show the most probable distance from the nucleus. But it doesn't show any of these 3 things. So just make sure you can kind of talk about that for essay questions. And that leads us to quantum numbers. So we did this in first year chemistry. They're actually a little bit more complicated, but the AP curriculum has taken out a lot of the quantum number discussions. So we're just going to go into them real briefly just so that you remember what these symbols mean. But if you do take college chemistry, they might go into more detail because, like I said, the AP curriculum has taken that out. So first of all, this is kind of like an electron's address. So this is the most probable location for finding an electron. It's going to be a series of letters and numbers, just like your address is a series of letters and numbers that tells the most probable location for the electron. Not the exact location, because again, we don't know the exact location. It's the most probable location. The first quantum number is going to be a coefficient. So if I have something like 3s2, the first quantum number is this coefficient right here. Can't draw an arrow, there we go. And this tells you the energy level or the distance from the nucleus. So this tells me that the electron is in the 3rd region from the nucleus. I picture them as circles, but they're not all circles, and I'll show you what the shape is in a minute. But if you can just picture them, like here's the nucleus. If we're doing a sphere, here's the 1st region, the 2nd region, the 3rd region. So that tells us the distance from the nucleus. The second quantum number is called sublevel. This is a fancy word for the shape, and there are 4 of them. We call them S, P, D, and F, and I'll have some pictures for you in just a minute to show you what they look like. But in general, an S looks like a sphere, a P looks like a peanut. It's more like just 2 lobes with it being skinny in the middle. D looks like a clover leaf, but if you call it double peanut, that'll help you remember what it looks like. So if you take 2 peanuts and put them perpendicular to each other, it'll look like that. And then F gets so complicated we don't even really have a good image for it. So this second quantum number right here is telling me the shape. So the combination of the 3 and the S together describes a region of space that we call an orbital. It describes how far it is from the nucleus. 3 is telling me how far it is from the nucleus, and it tells me what shape that region of space is. And then the little number up here that we're going to go into in just a minute is the number of electrons that are in that region of space. We can also talk about the direction. So an S only has one direction. You can only turn it one way and it's still a sphere. A P actually has 3 different directions, and you can think of it like X, Y, and Z. I can't draw the last one because it comes off of the screen and goes back into the screen. I'll draw it kind of diagonal, but if you picture it as this would be the PY, this would be PX, and then this would be PZ that comes off the screen. D, there's 5 different ones, and one of them looks completely crazy. I'll show you in just a minute. And then again, F is so complicated that we don't even know what it is. But what you do need to know is how many orbitals each of these has. So S has 1, P has 3, D has 5, and F has 7. So if you just remember the pattern, it's pretty easy to get that. And then when we talk about these orbitals, you can see that the maximum number of electrons per orbital is 2. You can't put more than 2. And so for an S, that's the most you can have since it only has 1 orbital. P has the X, Y, and Z, so you can put 2 in each one to get a total of 6, and then you can see the pattern from there. And then the last quantum number has to do with spin, and this says that if 2 electrons occupy the same orbital, they have to have opposite spins. And this is called Pauli's exclusion principle. We did this when we did orbital notation with the arrows that I'm getting ready to talk about in just a minute. So first of all, electron configuration is like an electron's address. It's going to be a series of letters and numbers that describes the electrons in an atom. So for example, this first one for germanium, the combination of the 1 and the S is describing a region of space. 1 tells me how far it is from the nucleus. S tells me that it's a sphere. And then that little 2 is telling me that there are 2 electrons in that region of space. If you move farther away from the nucleus, we get to the second one, so 2S, and then you can go on from there. Most of the time we abbreviate electron configuration because we really only care about the electrons that are on the very outside of the atom. Those are the ones that can be traded and shared and donated and stolen, and so we really only care about the ones on the outside. So we can abbreviate all of this. We can abbreviate all of that with argon, and then we can just show what's after it. And if you don't remember how to do electron configuration, you can go back to my review lessons that I did the very first day, and I think it goes through some of that. And if you still don't know it, just let me know and I can go into detail about how to do electron configuration. Orbital notation is where you do something like if you had 4p3 and you wanted to show those electrons, you should always show the number of orbitals first. So we have 3 because p always has 3 orbitals, and then you fill up the arrows. So we have 3 arrows, and don't forget that you're going to put 1 in each line before you come back for seconds. So it would be wrong for you to put 2 in the first blank and then 1 in the second blank and nothing in the third blank. And that's Hund's rule. Hund's fair share rule says that you have to put 1 electron per line before you come back for seconds, and that has to do with some electron repulsion. And then the last thing there is the ion configuration. So for example, notice that chlorine down here, if it's neutral, when you do the electron configuration, you go up 1 all the way over to the right, and that's where you get neon. You can put in brackets. Then you start with the element after neon. So 3s2, 3p5 would be for neutral chlorine. If you do it for chlorine's ion, you add that negative charge on it. That means that you're going to change the number of electrons, and negative means you're gaining an electron. So we're going to add 1 more, and it becomes p6. All right, this is really important because you did not do exceptions in first year chemistry, so you need to make sure you understand what the exceptions are for AP chemistry. So what this says is that full and half full P and D sublevels tend to be really stable. So for copper, if you write out the electron configuration for copper, you end up with 4s2, 3d9. Well, copper really wants to have a full D, and so what it will do is steal 1 electron from the S and donate it to the D. And it only does this for certain columns of elements. So anything on top of or below copper is also going to do this. Anything in that 3d9 will steal 1. Most of the time for the AP exam, what they do is they give you the data. They'll show you, what's going on with these atoms, and then they'll ask you why some of the data doesn't match what it's supposed to. So maybe they would say, this is the electron configuration for copper. Why is it like that? Why is it not what it's supposed to be? And so they want you to be able to explain these exceptions. So most of the time you'll use this not to come up with the data, but to explain why the data exists. And you'll go through some of these in your homework as well. These are the different shapes. I told you we have some pictures to help you. So notice that S is a sphere, P is a peanut, and you can see better on the axes there, the X, Y, and the Z axis, the different lobes for the P. The D gets kind of crazy. So the first 4 for D look like a clover leaf, and then notice this 5th one is just crazy. It's like a peanut with a donut around the middle, or a bagel. And that's just the picture that they have for it. And then F is so complex that we just don't even have a good visual image for it. All orbitals with the same value of N have the same energy. That is important. So what that means is any electrons in a 3, whether it's 3s or 3p, they're going to have the same energy. The lowest energy state is ground state. That does not mean that all of the electrons are in the first region. It just means that they're as close as they can get to the nucleus. So for example, if you have 3 electrons, you can only fit 2 in the first ring, and then it's full, so the third one has to go here. That is still ground state. So it doesn't mean they're all in the first ring, it just means they're as close to the nucleus as they can get. As they absorb energy, they can move to higher orbitals. So again, they can move away from the nucleus, and that's called the excited state, but it's really unstable. So it's most likely going to fall back to ground state pretty quickly. We talked about that an orbital can only hold 2 electrons, and they have to have opposite spins. So again, when you're doing orbital notation and you're drawing the arrows, you can only have 2 arrows per line, and they have to be opposite direction. So you will never have 2 arrows going the same way, and you will never have more than 2 arrows in a line. So both of those would be incorrect. And a lot of times on the AP exam, they'll give you pictures of various orbital notations and ask you which one is the correct one or what's wrong with one of them or something like that. So you just need to be able to understand the rules for how to set up those arrows. And the last thing is section 7.9. So when we talk about, so first of all, poly means many, electronic means electrons. So when we talk about lots of electrons in an atom, it's going to change things just a little bit. So we have lots of energies going on here that can affect it. So we have the kinetic energy of the moving electrons, we have the attraction between the nucleus and the electrons, and we have repulsion between the electrons. So all of those are used to explain why things happen in nature. So a lot of times if they say, you know, why would, for example, why does Hund's rule exist? So if we talk about, again, if we go to a 5p3, why would you not do this? And the reason is because of the electron repulsion. So they use those to explain various things in science. Shielding effect is a great thing to be able to talk about when you're, especially when we get to the periodic trends that we're going to do in the next section. So this is the idea that, I'm just going to draw it as a circle again. This is not really what it looks like, but we're just going to use this as a simpler model. If we're talking about this electron right here, what we want to focus on is the attraction of that electron to that positive nucleus. And the farther it is from the nucleus, the less likely it can feel that positive charge. But we also have all of this stuff in between. So all of these other electrons and energy levels in between, and it kind of blocks the positive charge from the nucleus. It's the same idea as if you put a lot of papers under a magnet, the magnet is not going to stick to your refrigerator as well. And that's called the shielding effect, and it's a great way to explain some of the periodic trends that we'll get to in the lesson for tomorrow. And the last thing is just